Question 5 is about a laser pen in A where to define the term phase difference. Well, this is the difference in degrees or radians between 2 points on a wave or between similar points on two waves. We also have to define the term coherence, and this just means a constant phase difference. In B, we have the laser sent through two slits, S1 and S2, producing a pattern. In part 1, we're to explain in terms of path difference why P is a bright line and Q is a dark line. Well, P is a whole number of complete wavelengths further from S1 than it is from S2, so the waves will meet in phase and will constructively interfere, whereas Q is an odd number of half wavelengths further from S1 than S2, so the waves meet in antiphase and will destructively interfere. In part 2, section 1, we're to use the diagram to find the wavelength of the light. Well, for this we can use wavelength lambda is equal to slit separation A times fringe separation x over the distance from the slits to the screen d. Putting in the values given, the slits are 0.56 millimeters, 0.56 times 10 to the minus 3 meters. The fringes, well, there are 10 of them, 42, making 42 mil, so 42.2 times 10 to the minus 3 over 10, because that is for 10 slits, and then we need to add d on the bottom here of 4.5 meters. This gives a value of 5.25 times 10 to the minus 7 meters. In part 2, we have to determine the percentage uncertainty in wavelength. Well, the percentage uncertainties will add because all these terms are multiplied together. And so we have 0.02 over 0.56 plus 0.2 over 42.2. This was our slit separation, this is our fringe separation, plus 0.02 over 4.5 for the slits to screen. We need to multiply all of that by 100 to make a percentage, and that comes out at 4.5%. In C, part 1, we're told the power of the green light is 50 milliwatts, and it's now used in a demonstration of the photoelectric effect. We're to calculate the number of photons the laser emits per second. Well, the number of photons times the energy of a photon, which is hc over lambda, will equal the energy per second. Number of photons per second equals the energy per second, which is the power. So we can rearrange for the number is equal to the wavelength times the power over hc, which is 5.25 times 10 to the minus 7 times 50 times 10 to the minus 3 over 6.63 times 10 to the minus 34 for the Planck constant times 3.00 times 10 to the 8 the speed of light in a vacuum. This gives 1.3 times 10 to the 17 photons per second. In part 2, we're told the green light falls on negatively charged metal plate with a work function of 2.6 electron volts. We're to explain whether photoelectrons will be emitted. Well, for them to be emitted, we need hc over lambda, the photon energy, to be greater than the work function. hc over lambda gives us 6.63 times 10 to the minus 34 times 3.00 times 10 to the 8 over a little bit more like a 3 over lambda of 5.25 times 10 to the minus 7. We also need to change this energy in joules to the energy of the work function we're given in electron volts. Doesn't matter which we change, as long as we change them both to the same units. So I'm now going to divide by 1.60 times 10 to the minus 19, which will transform this energy, which would have been in joules, into electron volts. That gives 2.37 electron volts. This is, so basically the energy is less than the work function of 2.6 electron volts, so no electrons would be ejected.